The headline promises designer superconducting diamond as the key to multi-modality quantum chips. That sounds like science fiction until you realize the real stakes involve heat and latency killing autonomous decision-making right now. You are about to learn how this specific hardware solves the thermal bottlenecks that force current systems into slow, heavy cooling loops. Think about a high-performance robot trying to navigate a chaotic environment in real time. Its processors generate massive amounts of waste heat during complex calculations. To keep functioning, traditional architectures must route that data through dilution refrigerators or extensive cooling infrastructure just to prevent thermal runaway. This creates a fundamental latency penalty because the system spends valuable processing cycles managing its own temperature rather than reacting to threats. The result is a robot that thinks too slowly for true autonomy, trapped by physics in ways we have not been able to overcome until recently. Researchers are now addressing this with a hybrid approach combining nitrogen-vacancy centers within diamond lattices and superconducting circuits. This creates what they call designer superconducting diamond, an architecture designed specifically to merge the best traits of both materials into a single functional unit. The diamond provides atomic-scale spatial resolution and room temperature stability for sensing magnetic fields with extreme precision. Meanwhile, the superconducting electronics deliver high-speed processing speeds that would normally require massive cooling systems if implemented in isolation. Here is the thing about this hybridization. It does not just add capabilities, it fundamentally changes how data flows through an autonomous system by eliminating directional dead zones and optical diffraction limits found in standalone sensors. When you integrate nitrogen vacancy centers with superconducting microwave cavities, you create a unified sensor platform that fuses high-resolution vector sensing with scalar field sensitivity. This allows the hardware to perform real-time multi-parameter decision-making without the sequential data processing delays that currently plague edge AI applications. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The experimental data supports this theoretical advantage quite concretely. Measurements confirm that this hybrid approach improves magnetic sensing accuracy by over 10 decibels compared to existing methods. A 10 decibel improvement is not a marginal gain. It represents a significant leap in signal clarity and noise rejection. This level of precision effectively eliminates the blind spots where current sensors fail, allowing an autonomous system to perceive its environment with a fidelity that was previously impossible outside controlled laboratory conditions. Now consider how this scales beyond a single chip. The architecture relies on modular designs utilizing superconducting indium bump bonds to connect multiple chips together. This method proves that scaling up to complex multi-chip systems does not degrade qubit coherence or relaxation rates, which has been the primary fear in quantum engineering for years. You can build larger, more powerful processing units without introducing thermal crosstalk or signal latency that would otherwise destroy the quantum state of your information. This shift moves us from fragile single-function sensors to modular tunable coupler systems, where superconducting qubits operate at scale. The elimination of thermal penalties means complex real-time quantum operations can occur locally on the edge device, rather than relying on remote cloud processing or bulky external cooling units. This is critical because it removes the dependency on dilution refrigerators, which are heavy, expensive, and fundamentally incompatible with mobile autonomous platforms like drones or self-driving vehicles that need to operate in diverse environments without a lab infrastructure backing them up. However, we must maintain intellectual honesty about where this technology stands today. While benchtop prototypes show remarkable promise, the specific phys.org report on designer superconducting diamond remains technically opaque due to corrupted source data regarding exact performance metrics for autonomous deployment. We know the theoretical framework is sound and the hybridization works in controlled tests, but the transition from laboratory proof of concept to mass-produced systems requires overcoming substantial production yield gaps that have not yet been closed. Current fabrication relies on precise atomic-level manipulation of diamond lattices, a process that presents manufacturing scalability challenges compared to established silicon-based workflows. Creating these quantum-ready diamonds involves manipulating individual atoms in ways that are difficult to replicate at an industrial scale with the high yields required for commercial products. Until we can standardize this production and achieve consistent quality across millions of units, the technology will remain confined to specialized research facilities rather than powering everyday autonomous systems on our streets or in our skies. The path forward is clear even if the destination is distant. The hardware solution is theoretically capable of reducing latency enough to enable true real-time inference for complex machines, because it solves the heat dissipation bottleneck that forces current designs into inefficient cooling loops. By integrating diamond stability with superconducting speed, we are building a new paradigm where sensors and processors work as one unified system rather than competing against each other through thermal constraints. This breakthrough suggests that future autonomous systems will not just be faster, but fundamentally more capable, because they can process sensory data at the atomic level without waiting for cooling cycles to complete. The multi-modality architecture leverages diamond's engineered properties to achieve long coherence times while maintaining low thermal resistance, directly addressing the physical limitations that have held back quantum sensing in practical applications for decades. We are standing on the edge of a new era where machines can think with the speed and precision required for true autonomy, provided we solve the manufacturing challenges before scaling up production. The gap between sci-fi expectations and reality is closing as we move from theoretical models to functional prototypes that demonstrate real-world performance gains in sensing accuracy and thermal efficiency. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.